She wants her Barbies from Dona. All right, ladies and gentlemen. So we are going to continue on with, so many things are happening right now, with energy. Okay, so we have to review a little bit of energy in general before we can actually move on to the nitty-gritty of it and the newer material. So if you're following along, you're on review book pages 82 to 98. That's your review book, topic 5. You guys did your vocab yesterday, right? So some of these words should sound very, very, very familiar. Also, I've been saying it all year, but if you ever want to get ahead of yourself so that you know what we're doing, I always say you should probably try reading the chapter ahead of time. It's not that many pages, and if you look, most of the pages are practice problems anyway, so you might want to read and outline it. I'm not collecting it, but it will help you when we start doing the chapter itself. This chapter is only like 4 days long, and then we do a lab with it. I don't know if we're going to be able to do the lab physically. I'm going to try and do it from home and demo it, so at least you guys can see the difference, okay? And it'll make more sense. Okay, so let's talk about energy. First of all, energy is the ability to do work, right? Yesterday morning specifically, I was exhausted. Tuesdays are always worse coming back from a break than Mondays are. I've learned that a long time ago. Until I finally sat down and ate something, right? My ability to do work was 0. Why? Because I had no energy. By eating something, I actually fueled my body and I was able to get up and teach. So energy comes from different things, and it also exists in a variety of different forms, okay? Can you guys name some? Do you know what types of energy there are? You learned 2 in my class. I know that much.
Heat, mechanical, kinetic,
right.
What's the other one?
Potential, right? Electromagnetic, all those fun ones, right? So it's a whole bunch of different types of energy. Well, specifically, we're going to start off with electromagnetic, okay? Now, when you have electromagnetic energy, right, it interacts with the environment differently, all right? There's reflection, refraction, scattering, or absorption. I like to still think about it. Okay. Let's see if it doesn't show it as much as this part. Okay, so reflection is exactly what it sounds like, right? It hits it and it bounces back. You should know that by now. Refraction is, and I'm trying to see if, I can't really see it that much. I saw it better yesterday. Now you can kind of see it. Can you guys see the straw, right? Here's my straw in my water, right? When I put it in the water, it kind of looks like it moved to the right, or my right, a little bit. You guys see that? And the reason for it,
Yeah.
right, it kind of looks like it went like that, right? If this is the straw going in, when it got into the water, it looks like it went like that, right? What happens is that the light inside is being refracted a little bit. So when, from your perspective, it looks like you've shifted part of it, or that part of the straw has broken off, but it actually hasn't. Okay. Scattering is what it sounds like. Okay. Have you ever heard the term, you're like cockroaches when the light turns on? You ever heard that before? Right? Oh, and what does that mean?
Well, when a light turns on, all the cockroaches scatter in different directions.
Exactly. So they move in different directions, right? So electromagnetic energy can also do that. Even though you're shooting it straight, they can branch off into 15, 30, 100 infinite different directions, okay? And then we have absorption. Absorption is when you take things in. Does anybody need me to go over any of them again?
Could you go over transmission one more time?
Which one? Transmission, refraction?
Yeah.
Okay, so it's when, if you're looking at So look at my straw. Oh, let me take this off. Right? My straw is straight, right? But when I put it into the water, it kind of looks like it moved. Not so much today, but it was better yesterday, probably because it wasn't seltzer at the time. So when you put in an object that's straight, it kind of looks like it goes like this. That's kind of what refraction is. Okay, so now we went over what happens when electromagnetic energy will interact with the environment. Now I want to talk about the properties that affect the absorption or radiation of electromagnetic energy. And the two major factors are color and texture. So those are the two major factors. My daughter's no longer here. I can shut this off. Okay. That will affect how electromagnetic energy is either absorbed or radiated. Okay. All right. So, color. Why is color important? Well, I want you to think about it. When we're talking about energy in general, you guys mentioned heat energy. Okay. In the middle of the summer, when it's 105 degrees outside, what color clothing should you wear?
White.
Why?
Because the sun absorbs dark colors like black.
The heat gets absorbed into the dark colors. Exactly. That's the same thing here, okay? When you are looking at the absorption or the radiation rate, remember, absorption means to take in, radiation means to go away, okay? It's kind of like reflecting, okay? If you want to take in more energy, whichever type it is, you're going to have a darker color. Now, you should absolutely star this part of your notes. This shows up in like 6 other chapters from now on. Okay, this concept right here. All right. The second thing is texture. You have rough versus smooth. Okay. Does anybody in here have the private lessons downstairs with the music department where you go or you go to practice in those soundproof rooms? Anybody ever been in a soundproof room or a recording studio or seen a recording studio?
A coke chamber?
Sure. Like it's the soundproof room, right? Leanne,
Yeah, it's really weird on your ears.
Right, but what color are the walls?
It's like a gray.
They're like a dark gray, right?
Yeah.
And are they smooth like marble?
No, not really. It's like,
What?
I'm not sure. I don't really remember. I haven't been in there in a while.
Okay, I'm hoping you're not going the furry wall, the furry wall.
Aren't they like funky or something?
They're
Like,
what?
aren't they like?
Yeah, that's right. They're like it's like
Yeah, they're more chalky-ish.
Huh?
yeah, it's like a
They kind of look like the inside of a panic room.
Yes, or the inside of an egg carton. Right, if you took an egg carton and put it to its side, right?
Pretty much.
Like
yeah, the little
the kind of things,
Mm-hmm.
right? So you're telling me that inside of a soundproof room, the walls are darker, and they're rough, technically, right? They're not smooth. They've got some texture to them, right? Those walls absorb sound. Okay, because they're darker colored and they are rough. Okay, because of those two things, you're going to get more absorption. So the other day before Christmas, when it snowed, right? You guys probably had to go outside and shovel at some point, or maybe you just went outside. Okay, I know we had school, but you probably still had to go outside and shovel, right? When you went outside and you saw that bright white snow, that looked like it was very serene and very smooth. If you looked directly at it when the sun was out, you got blinded. Why? Because white and smooth surfaces reflect that light like a mirror. Okay? So whenever you're looking at anything like this, if it is a dark color and rough, it's going to absorb more. If it is a light colored and smooth, it's going to reflect more. And if you want to think about it, you can also think about the lab, right? The earth science lab, or even the chem lab across the way. The chem lab is all white. Every surface is smooth. The desks are smooth. The walls are smooth. There's no texture to them in any way, shape, or form, which is why when Mr. Petrie is talking, or Miss Jimenez is talking across the hallway, I usually have to go over and shut the door a little bit, because the sound will just bounce all over the place. And since we don't close the doors anymore, they have to, it ends up coming into our room since we're right across the hall. Okay? All right, so let's talk about kinetic energy versus potential energy. This should be a review for you because of the fact that we've done this before. So kinetic is the energy of motion, where potential is the stored energy. Okay, so you have the energy of motion, and then you have the stored energy. All right, now keep that in mind. All right. Transformation is when you go from one type of energy and it transforms into another, right? When you were looking at this waterfall, you see how all the water molecules at the top of the the waterfall are kind of packed together, but then as you go down, they become more and more misty, right? Like they kind of go far apart. That's because you're going from potential to kinetic. Okay, because you're not really moving, and then you speed up here, and you're moving a ton. So it's just transformation goes from one to the other. Okay, so for those of you who are planning on going to chem next year, you're lucky, because I'm about to show you something that is going to be, I'm going to teach you a bunch of chem concepts. All right, I'm going to give you more background information. And for me, earth science is one of those subjects that kind of throws all of the sciences together. And if you don't have the background information, then a lot of this doesn't make sense. Okay, so thermal energy we also refer to as heat. They go hand in hand. However, this is not the same thing as temperature. Okay, temperature and heat are completely different. You think I'm serious? I mean, I have like 40 exclamation points after this. All right, so heat and temperature are two different things. Now I'm going to explain the differences. All right, heat is going to be the total energy, where temperature is going to be that average kinetic energy. Okay, so heat is going to be the total energy, where temperature is average kinetic energy, so the energy of motion. The units for heat are joules, or capital J. Okay, for temperature, we deal with mostly degrees Celsius and Kelvin. Okay, yes, for temperature, there is a degrees Fahrenheit. However, in science, we don't really deal with that. Okay, for heat, we're dealing with an actual energy value. Okay, for temperature, we're saying how hot or cold a substance actually is. So it's two entirely different things. Now, I explained this to you earlier in the year, but just in case you forgot, number one, for this class, even though I told you that you can convert, and I gave you the formula on how to convert from degrees Celsius to Kelvin, okay, for us, we have this page on the reference table where you don't have to memorize it, where you don't have to memorize what temperature does water freeze or melt at, because it's both the same temperature, or water boils or condenses at, because they're listed for you on your reference table here. Okay, a couple things to point out, like we've done earlier. Each one of these tick lines on the left-hand side are worth 2 for Fahrenheit. For Celsius and Kelvin, they're worth 1. Okay? All right, page 13. We did all this already. All right. So, here we have a round bottom flask, which you cannot leave on a table because it will spill over. Okay? And it's filled with some sort of liquid. Inside of liquid, there's this molecules. Now, I over-exaggerated the molecules into these giant red balls, basically, okay? And we have our thermometer. So what's going to happen? If I heat up, stop, Raj. If I heat up the liquid, the molecules are going to start to move, okay? When you add energy to it, right, you end up making the molecules move more, which eventually they start hitting the thermometer. Every time that they hit the thermometer, the now increased kinetic energy gets transferred to the liquid in the thermometer, the alcohol that's in the thermometer. Okay, these are the old school thermometers that we use in class. Your parents may or may not have one of these thermometers, and they usually shake it before they take your temperature. You guys mostly have digital ones now, but this is how it actually works. Okay, that's why the digital ones are not always the greatest unless you put them in your mouth, because when the molecules are moving faster, they hit the actual thermometer, which increases the temperature. Right, so there you go, there's an increase in temperature. Why? Because their energy is transferred, okay? It comes down to that energy transfer. Okay, so the molecules that are inside the liquid gain energy from you heating up the round bottom flask. They start to move more because they gained more energy. They start to move more and they start to hit the thermometer. Every time a collision occurs, there's a transfer of energy. Does that make sense?
Yeah.
You guys okay with that? All right, so the more they do this. Okay, so first off, if this is a gas in an open container, all right, if we start to move more, first of all, it's cold versus hot. Which one is moving more, the cold molecules or the hot molecules?
The hot?
Right, exactly, because they have more energy and therefore they are moving more, right? So first off, energy gets transferred from that heat source to the molecules. As they transfer more and more heat, the molecules move more and more and eventually will escape out of the container, right? Here we go. Okay, now the thing is, when they're escaping, the reason that they're escaping is because, notice the difference. Look from the beginning, right? The cold molecules are closer together. If they are closer together, what happens to their density?
It increases.
Right. So cold substances are going to be closer together, which means they're going to be more dense and they're going to sink. That's why cold air sinks. Okay, I'll say it again. So in cold substances, the molecules are going to move closer together, which increases their density, which makes them sink. Okay, whereas on the hot substances, you noticed that over time they started to escape. Why? Because when you're heating them up, they are moving faster, which means they are spreading further apart, which means their density decreases and they rise up. Okay, so the more energy that they have, the further they spread apart, the less dense they are, and that's why they rise. Okay, so when you heat up the substance, they gain more energy, which means that they move more, which means they become less dense, and the molecules will rise up. That will come into play a lot. All right, so I've joined you here. Specific heat. All right. Specific heat is a concept that is hard for you to actually understand. So please pay attention. Sometimes it can be a very hard concept. All right. So what specific heat is the amount of energy it will take to raise the temperature of a 1 gram substance by 1 degree. Let me know when you guys have that down.
I'm finished.
Give you guys another couple of seconds. All right, you guys good?
Yeah.
Yeah, I'm good.
Anybody still writing? Okay. All right. So we use the formula Q equals MC delta T. Make this bigger. This is what's known as the specific heat formula. Q equals MC delta T. Okay, where Q is going to be our heat value in joules. Okay, M is going to be the mass in grams. C is going to be the specific heat capacity. All right, and delta T, the triangle T, delta is the triangle, means change in temperature. Okay, anytime you see that triangle, it represents, you've seen it in math at some point too, right? We did the change in y over the change in x, right? For the slope formula. So delta is always going to be the change. So it's always going to be the final minus the initial. So when we were doing the slope formula, it's y2 minus y1, right? So it's the second minus the first. In science, we call that the final minus the initial. Okay? Now, the thing with specific heat is every substance has a different specific heat value. Okay? The ones that you need to know are on page 1 of your reference table. Okay, you don't have to memorize them. You just have to know that they are there. And it's page 1 of your reference table. And I want you all to be looking at it, which is what I'm doing as well. Okay, you will notice that they're all over the place. They go from liquid water at 4.18 joules per grams degree Celsius and lead at 0.13 joules per grams degree Celsius. What that tells me is that lead is going to heat up way quicker, okay, and need less energy and less heat than something like liquid water. Now, you are not responsible for knowing how to do the math. However, I am going to show you, and I'm going to prove this to you. Okay, we're going to skip that for now. All right, so let's say I have a, let's go with a, okay, we'll go with a 10-gram sample of water. Right, versus 10 grams of lead. Okay, I want to change the temperature of each of them by 50 degrees Celsius. So what that tells me is the only value that is different between the two of them is going to be their specific heat. Okay, so when I do the math, Q equals MC delta T. I both have a 10-gram sample. Their specific heat is different. But I want to change both of them by 50 degrees, right? So we know that degrees Celsius is going to cancel, and we know that grams is going to cancel, right? So when you do the math, right, we have 10 times 4.18 times 50. For water, we need 2,090 joules of heat. Okay, don't worry, I'll show you this again in 1 second. For the lead, right, in order to heat it, the exact same sample by the same amount in temperature, right? We want it to all be 50, yes? All right. Grams cancels. Degrees Celsius cancels, and we're left with joules. So 10 times 0.13 times 50 is 65 joules. What does that show me? That shows me that you need a ton more heat to heat up the same amount of water as you do lead, right? You need 2,090 joules of heat to heat up the same size sample of water compared to the same size sample of lead, right? Because that specific heat capacity changes everything, all right? The lower the specific heat, the less energy of heat you will need to heat up that substance. And guys, that is the end of the period. I will start tomorrow with a little video clip explaining this a little bit more. Okay, does anybody have any questions? All right, guys, have a good day.
Have a good day. Bye.
Have a great day, Miss Gonzalez. Bye.